Hello and welcome to 12.7 Notes. Today's lecture is on finding surface area and volumes of similar solids. So first we need to discuss the definition of similar solids. Two solids of the same type with equal ratios of corresponding linear measures such as heights or radii, right? Anything that can be measured in like feet, inches, yards, meters, things like that are linear measures. So they have to be of the same type, these two solids, and they have to have equal ratios of corresponding linear measures, such as heights or radii, are called similar solids. Okay? And the common ratio is called the scale factor of one solid to the other solid. Okay? So please write this down and get caught up. Remember, you're in total control of this presentation, so you can fast forward or rewind or pause it. Do whatever you'd like. Remember, you're in total control. But for the sake of this presentation, I will continue. And this next part that I've written in blue is really important. It's what you're going to be using to solve these types of problems. So if two similar solids have a scale ratio of A to B, then corresponding ratios do not have a ratio of A to B. They have a ratio of A squared to B squared. Okay? And corresponding volumes do not have a ratio of A to B. They have a ratio of A cubed to B cubed. This is extremely important. Again, if the linear ratio is A to B, then the area ratio is A squared to B squared, and the volume ratio is A cubed to B cubed. That's so important that I need to cover that a little bit more. Obviously, I'll cover it a lot more in class, and I have a demonstration that can really solidify this point. But for now, I'll just try this here. Let's say you have these two similar solids, okay? And this one has a certain radius, and this one has, of course, a different radius, because one of these solids is larger than the other. And I don't know what these two, radii, or the two radiuses, right, the two radii are, but let's say they're in a ratio of A to B, for example, whatever. It's like 9 to 14, or 6 to 7, or it doesn't matter. But for the sake of this argument, they're in a ratio of A to B. So that means their linear ratio is A to B. But the ratio of their areas is not A to B. So if you wanted to compare the area of this solid with the area of this solid, you do not use A to B. You would have to use A squared to B squared. And if you want to compare the volume of this solid with the volume of that solid, you would have to use A cubed to B cubed. Okay? So as another example, let's just say for sake of argument that the linear ratio is 3 to 4. And let's say I want to compare the two areas, the area of this versus the area of that. In other words, maybe I know the area of this one is, like 24 square feet or something. What's the area of this solid, right? So if I wanted to do something like that, and all I knew was the ratio of linear measurements, and say if it was in a ratio of 3 to 4, but I want to know what the area is, I cannot use 3 to 4. I'd have to use 3 squared to 4 squared, or 9 to 16, okay? I would have to use a ratio of 9 to 16. And let's say I want to compare now the volume of the smaller object to the volume of the larger object. Again, I could not use 3 to 4 or even 3 squared to 4 squared. I have to use 3 cubed to 4 cubed, okay? Which is 27 to 64. So if the ratio of these two radii are in the ratio of 3 to 4, just as an example, then the ratio of their volumes is not 3 to 4, it's 27 to 64. It's the cube of each one. It would be A cubed over B cubed, okay? And that's really important. You need to remember that in order to solve these problems. If you tried to compare volumes, but you used the linear ratio instead of the volume ratio, you would get the wrong answer. So you got to be really careful, okay? We'll see what types of problems you can get with this type of material in the next frame. And here we are in the next frame. So please copy down this prompt. Cube C is similar to cube D, not shown, with a scale factor of 3 to 5. Find the surface area and volume of cube D. And here's cube C. And cube C has a surface area of 54 square inches and a volume of 81 cubic inches. So if we know the surface area and volume of this cube C, and we know the scale factor, then how do we find out what the surface area and volume of cube D is? Okay? And the way you do that, let's start off with finding surface area, is first you have to know what the linear ratio is. Well, the linear ratio is given as 3 to 5, so that's where I get the 3 to 5 from. But I'm trying to find surface area. I'm trying to find the area. So I'm trying to compare this area with the area of cube D, the unknown. I cannot use this ratio of 3 to 5. I have to use the square. So I have to use the area ratio, which is 3 squared over 5 squared, or 9 to 25. That's the ratio I will use to compare areas. Okay? So, in order to compare the area of C to the area of D, I have to use 9 over 25. Okay? I have to use 9 over 25. If I used 3 over 5, I would get the wrong answer. So I have 9 over 25, and I could say that that's equal to 54 over x, right? Because the surface area of cube C is 54. And so what is the surface area of cube D? Okay, so this is the proportion that I'm going to use. If I used the linear ratio, I would get the wrong answer. That would not work. That is wrong. You do not do that. That is wrong. You cannot do that. I cannot emphasize that enough. Okay? So we have to use the area of the ratios, which is 9 to 25. Okay? And then from here on in, I think the rest should be no problem. We have a proportion, and then to solve the proportion, you cross multiply and get 9x is equal to 54 times 25, or 9x is equal to 1350. You divide both sides by 9, and you get x is equal to 150 square inches. Okay, 150 square inches. And to find volume, you need to use the linear ratio. You need to go back to the linear ratio, which is again 3 to 5. But to compare the volume of cube C with the volume of cube D, you cannot use 3 to 5. You have to use the volume ratio. And the volume ratio is 3 cubed over 5 cubed, right? And that would be then 3 cubed is 27 and 5 cubed is 125. So you need to use the ratio 27 over 125. So the volume of C compared to the volume of D would be in a ratio of 27 to 125. Okay? And since everything in the numerator refers to C, then we have C on the top. So I'm going to be putting the volume of cube C on the top here. This would be the volume of cube C, and this would be the volume of cube D, right? Everything on the top has to do with C. Everything on the bottom has to do with D. So this is C, C, and C. Everything on the numerator has to do with cube C. And then everything in the denominator has to do with cube D. That's why you put the 81 here in the numerator, and this x, this unknown, in the bottom because it's the volume of cube D, which goes in the numerator. Okay? So this is my proportion. This is the proportion that I'm going to be using. This is good to go. Okay? That's good. If you used this ratio, you would not get the right answer. That is not correct. That would be wrong. You do not do that. Okay? So again, we have to use this ratio here. So let me erase these things here and get back to our task at hand, which is using this proportion. And then again, once you have the proportion, you cross multiply and you get 27x is equal to 125 times 81. 125 times 81 is 10,125. You divide both sides by 27 and you get x is equal to 375 cubic inches. Okay? So that's the end of the lecture. If you have any questions, as usual, please feel free to contact me at your convenience, and it would be my pleasure to help you. Okay? Bye-bye.